All right, quiet, rainy day. So I have some good news. I had a meeting with Ashvin yesterday. So lab 3 is pushed back another week. So you have 3 weeks for it. Lab 6 is deleted. So there's be no lab 6. And then what we're gonna do is I'm creating a new lab 4 that is going to be on pipes and making processes and all that fun stuff. So this will be my creation of a lab, so hopefully it will be fun and doable. So I guess we'll see, so you'll have a flavor of what I do for labs. And then for the last lab, the web server one, we're not gonna make them depend on each other anymore, so we'll give you a threaded server with maybe a bug in it, and then you'll have 3 weeks to do the last lab, which is like a combined lab 4 and 5 that's currently on the website. So that will hopefully make things more doable. It stops, there being a lab due when there's a quiz. So also the other class is kind of behind. So the scheduling stuff is not going to be on the quiz. So the quiz is going to be processes, threads, locks, and all the fun questions you can ask for that. So next week we have kind of free. So early in the week, I'll do like a lab 4 primer where we'll have an example, we'll use a pipe, and we'll kind of see how to use some of the tools you'll need to use for lab 4. And then other than that, for next week, we can do review or just let me know on Discord what you want to see. I'll go through Ashvin's stuff again to make sure we're not missing anything. But if we want more practice on threads, processes, locks, we can do that next week. But while we're at it, let's just wrap up scheduling. So after the next week, when we have our quiz, we can go into virtual memory and all that fun stuff and actually learn what an MMU is. So we talked about scheduling before. It was fairly basic. We ended off doing round robin. And today we're going to, one of the comments last time was, well, what about if we added something like priorities? So we can add priorities. That seems like a good idea, but it's also going to complicate our life. So if we add priorities, that means we want to favor some processes over other processes. So if you assign each process as priority, then you have to decide what you want to do with that. Do I always want to run processes at a higher priority, or do maybe I just want to run them for longer, or what does that even mean? So if you do decide to just run higher priority processes first, you could just round robin all the processes of equal priority, and then after those are all done or sleeping or blocked, then you can move down to the next lowest priority and round robin all of those and go through that, and that is one valid thing you could do. So when you add priorities, you have to give them a number. The easiest thing to do is just assign a number for a priority, but then you have to pick, does a higher number mean a higher priority, or does a lower number mean a higher priority? So the way Linux decided to pick it is they decided that the lower number means it is a higher priority. So for normal processes in Linux, if you see a -20, that is the highest priority for normal processes, and a 19 is the lowest priority. So when you have priorities, that also might lead to starvation that we touched on last time. So if you always schedule processes with a higher priority, then you may starve lower priority processes. If there's enough higher priority processes that take up the entire CPU time, then you might starve lower priority processes because they just might never run, which would not be fair, and you can just starve them out. So if you want to avoid that problem, if you're the OS, one thing you could do is you could dynamically change the priority. So if a low priority process hasn't been executed in a very long time, you could temporarily bump up its priority until it finally gets to execute, and then after it executes, you can reset it back to its original priority. Or you might lower the priority of a process that's been hogging the CPU. Either way is a solution. Yep.
Why did Linux choose -20 to 19? That feels like such a silly range.
Just because. I don't know why they picked this range. It's a range of 40. We'll see it gets weirder. We'll see like a normal range. We'll see it. It's just weird. historical reasons. I don't know why exactly it was 40. They figured 40 was enough. So now that we have priorities, another new issue we have is something called priority inversion. So you can accidentally kind of change the priority of a process. So you can accidentally change a low priority process to kind of behave as a high priority process, and that's caused by dependencies. So if a high priority process depends on a low priority process, well, if it just yields its CPU time away and you always prioritize the highest priority process, well, it'll just get woken up again and again, and it's waiting on a low priority process. The only way to actually break that dependency is if you schedule the lower priority process as a high dependency process, because a high priority process is depending on it. So that's one solution. It's called priority inheritance. So if you detect that one process depends on another one, then you would want to make both processes have whatever one has the highest priority. So you just inherit the highest priority number between the two processes. And the kernel is going to be able to detect this, because if there's a dependency between two processes, they must be communicating together. And we know that all communication has to go through the kernel. So the kernel can actually detect a dependency. So if there's two processes that are communicating together, then it would make them the highest priority of the two. And then, of course, it would also have to do this recursively to chain across multiple dependencies if they were needed. So if A depends on B, and B depends on C, and C depends on D, and A is a super high priority process, then the kernel would have to make all of the processes temporarily a high priority. And then whenever that dependency is broken, it could revert them back to their original priorities. So that is how we would deal with priority inversion. So another thing you might do when you do scheduling is, well, you might want to separate the processes into two categories. A common historical way is to change them into foreground processes and background processes, where a foreground process is connected to a terminal, which is something that you type on and you see the results for. So any foreground processes are ones you are literally typing into, and you would want them to be more responsive, while background processes are something you don't interact with, which are probably going to do computation. So maybe you don't care about response time for those, and you actually just want them to be completed as quick as possible. So maybe you want to reduce the average waiting time. So you separate your processes. One cares about response time, one cares about average waiting time. So you could use a different scheduling algorithm for both of these types of processes, just because you have different needs for both of them. So that's one thing you could do. And then if you do that, you essentially have multiple queues for each processes, and you schedule them differently. So for all your foreground processes, you could just use round robin because you want good response time. And for all your background processes, you might just use first come, first serve, just to make the scheduler as easy as possible to implement and just make decisions as quickly as possible, and then reduce the number of context switching you have to do, because it's just some long running computation. You don't actually care when it finishes. But now you'll still only have like one processor on your machine, and now you have to schedule between queues. So maybe you round robin between foreground and background process, or the foreground and background queues. Or maybe you want to do all the foreground processes as a higher priority than all the background processes. And so your foreground queue is a higher priority than your background queue. There's all types of options you can do once you try and optimize things in scheduling, because there's no clear answer, and every process has different demands and what they care about. So there's no right answer, only trade-offs. Unfortunately, that is our lives as engineers. And we haven't even talked about scheduling for a system with multiple cores on it, because it gets even worse. So we'll assume symmetric multiprocessing. So that's SMP, which is what the kernel says. So it's SMP preempt. So what SMP is, it assumes that all CPUs are connected to the same physical memory, so they all access the same physical memory, and that they have their own private cache, at least at the lowest level. So at least they have their own L1 and L2 cache. There are systems where CPU cores are not all connected to the same memory, and programming them is very, very fun. Not really. Oops. So we'll just talk about a normal system that assumes all CPUs are connected to main memory because that just makes our lives infinitely easier. So if you have multiple CPUs now, well, I could just use the same scheduling algorithms we talked about and just tweak it slightly. So I just maintain only one scheduler. It could be first come, first serve. It could be round robin. And instead of just picking one process to run on one CPU, I will keep picking processes off using the normal round robin and giving them to the next available CPU until I utilize all my cores. So that's one easy solution. Yeah.
There's never like a kernel that like say that has like four CPUs. It just uses one of them to run itself to make sure everything's running and then just optimizes the three other ones? Or does it always like turn itself off at some point?
So the question is there a kernel that just takes over a single core and just stays there?
Well, because you could be doing like the scheduling maybe a little bit more efficiently because you don't have to like constantly change context to get the kernel running. Because it's always there, making sure everything's running quickly.
Yeah, so you could, I guess, have the kernel just only execute on one CPU core forever. Would you use that system? Would you install an operating system that if you have like a 4-core machine, you can only use 3 now?
Okay, so it does slow it down too much.
Yeah, the goal of the kernel is just stay out of the way and let you run your applications, because really that's all anyone actually cares about, right? The kernel's job is just to be transparent and let you run your stuff and essentially get out of the way. But that's something you could do, but I don't think anyone would use that kernel, unfortunately. So if you do this and just do round robin or something and just chuck it on CPUs as they're available, well, you get good CPU utilization because you're just feeding all the CPUs any running processes they can, and it's pretty fair to all processes. Like you could just use round robin between it. But the disadvantages of this is it's not going to be scalable because we only have one scheduler, so there's essentially one global lock around that scheduler that is divvying up, putting the processes on all the CPUs, so there's only one thing making the decision. And the other problem is it has poor cache locality because when you context switch processes, they might swap what CPU core they're actually executing on, which would invalidate all their caches, and it would have to repopulate them again, which is going to be slow. But this scheduler is the first real schedule we'll see. It was used in Linux in 2.4, which if you look at the timeline, that's probably like how old is it at this point? It's probably like 40 years old at this point, but this is one scheduling algorithm that was actually used. So we've seen our first real scheduling. But, oops. A better solution would be that, hey, if having one scheduler is bad, and that creates a global lock, if I have a bunch of CPUs, maybe I want a scheduler just runs independently on each CPU. So then I don't have to put a lock or a mutex along it. I know only one CPU has one scheduler, and it doesn't have to fight. They're completely independent. So you could do that. So each CPU just has a round robin scheduler that it keeps track of. And then when there's a new process, the scheduler's only job is to just assign it to a CPU. So if you have, 8 or 4 cores and 8 processes, then the global scheduler would just put 2 processes on each core, and then they would stay on each core for as long as they're running. So this is easy to implement. It's just, you just do the same scheduling you just did, but just once per core, and you just have to, decide what core a process goes to. It's also scalable because everything's independent. It's got good cache locality because all the processes stay on their CPU. So if you had like a super long running process that's doing some computation and it gets context switched out and it switches in something like ls that doesn't do that much, most of your cache would still be intact. So when you context switch back in that process that's doing this big computation, a lot of your cache would still be valid and it could just keep on running and doesn't have to repopulate the cache, so it would be actually really, really fast. The disadvantages of this is you might have some ridiculous load imbalance over time as processes come and go. So if you just have one CPU core that's happened to get all the very short running processes on it, it might be that it finishes all those processes and all the long running processes are on all the other cores. And if you can't if all the processes just stay on their core, there'll just be one core that's idle now that's not used. So it's not going to be able to use all your CPU resources as they kind of come and go. But you can make a compromise. That sounds like it has a fairly easy solution. You can detect if there's an idle CPU. So you'd have a global scheduler that essentially rebalances the per CPU cores. So if one of the CPUs are idle, it can just take a process from another CPU, which is called work stealing, and just give it to the idle CPU so it has something to do. But if this happens, you might actually want some say as into what processes can actually switch cores. So you might want some control. If you have a process that you know is really, really sensitive to its caches, then maybe you don't want that process to switch cores, and you would prefer that if it executes on a core, it stays there, and maybe you have some other process that you don't care about if it switches. So the configurable option for that is called processor affinity, which if people are using Windows at some point, if you go into Task Manager, that's one of the options you can see. If you right-click on a process, you can set its affinity. And basically that means the preference of that process just to stay on a single core, which will essentially get you some better performance. So if you have, I don't know, like a game or something you really, really care about performance, you could just essentially set it to only run on one core and not move, and then it would maintain its cache better. So you're sure it doesn't move. So this is another scheduling technique that is actually used in the Linux kernel. This is a kind of simplified version of the 01 scheduler, and that was used in Linux like 2.6, which now we're like only 30 years old at this point, which is actually pretty good. Oh, okay, and now an aside, if you get into like super high performance computing, there's another strategy called gang scheduling, which is another unfortunate term. So you might be in the situation with high performance computing where multiple processes, you have to schedule them all simultaneously. So the scheduler on each CPU can't be independent because I have, 8 processes I want to run all at once and all together. So gang scheduling is also called co-scheduling, and you need to schedule all the processes simultaneously so they essentially just act as one big unit. So it just requires a big global context switch across all CPUs to change them all more or less simultaneously. And that is something you'll only really see when you get to like high performance computing. So another difficulty is something called real-time scheduling, and that's yet another problem. And real-time just means that there are some time constraints, either a deadline or some rate you need to maintain. For example, like audio, there is a set frequency that you need to maintain in order to fill up some audio buffer on like your sound card. And if you don't maintain that, your audio will just sound like garbage. It will be all garbled and you just won't run fast enough to get good audio output. And so that's a really common one. Another one is like any autopiloting software, like on a plane, if you need to make a decision within a few microseconds or a few nanoseconds, that's something you actually care about for a plane. If you miss the deadline and the plane crashes, you can't just say, oops, sorry, I missed the deadline, my software ran a bit slow. So you actually need to provide some guarantee that you can actually hit your deadlines. So a hard real-time system does provide a guarantee, and you have to guarantee a task completes within a certain amount of time. Typically, this will only be done for like little embedded chips where you can actually count the clock cycles for everything, and it's doing something really, really simple. So you actually have to count the clock cycles, and it would be a simplified processor where you can understand what happens with the cache. So you'd have to assume like, all the caches are cold. I count the number of cycles that it could take, and hey, it runs within, 10 milliseconds or something. So I know I can hit this deadline. That is really hard and kind of annoying. So what people typically do, and you can imagine counting cycles, especially with something running on the Linux kernel or running on a modern CPU that has multiple levels of cache, associativity for the cache, different pipelines and all sorts of stuff going on. You can't actually provide any guarantees because it is going to be way too complicated. So for essentially anything running on like the Linux kernel, it's something called soft real-time, where it's just always hit in practice. So you just give critical processes a high priority, and you just figure out, hey, the deadline's always met in practice. So when you have a system that's essentially overkill, so you have like a 5 gigahertz chip on your machine, and you only have to, fill in a few hundred bytes every few microseconds to your audio chip, well, it's going to be fast enough that you don't really have to argue about it. It's always met in practice. And so Linux does let you do soft real-time, and we'll see kind of examples of that, because there are some threads on your system that are running as this real-time priority. So Linux, in addition to the scheduling we've already talked about, it actually implements first come, first serve and round robin, and they're actually useful scheduling algorithms are in use. So if you are sadistic enough like me and you want to search the Linux kernel source tree, you can look up Schedge FIFO, that's first come, first serve, and then round robin is Schedge RR, and you can see exactly how they implement it, or you can even change your processes to use this type of scheduling if you want. So what they do is just they use a multi-level queue if it's like a soft real-time scheduling for all the processes of the same priority, and it lets the kernel itself dynamically adjust the priority to be a bit more fair. But the way there's going to be on Linux, there's going to be two types of processes. There's going to be soft real-time processes, and those are always scheduled first. So they always schedule them at the highest priority, and they'll use something simple that you can argue about, like first come, first serve, or round robin. And then normal processes are going to kind of essentially adjust their priority based on aging and use, at least back in the day, the two strategies we just discussed. So this is where it gets weird if you actually, oh yeah.
So for Linux, are you saying they're using both of them, or like sometimes it uses one of them, sometimes it uses another one?
So you get the choice. On Linux, your process can be soft real time, or it can just be normal scheduling.
What if you don't? Wait. So soft real time is normal. But what about like the first come, first serve and then round robin?
So first come, first serve and round robin are choices for scheduling soft real time.
Okay. And you as a writing the process gets to decide what Linux does with it, or?
Yeah, you can say what it uses. So I think by default it uses round robin, but you can change it if you want, and you can set priority as a process. And we'll see what some processes they're doing. So the soft real-time processes are always going to be prioritized, and this is where it gets weird if you want to read the priority numbers on Linux. So soft real-time, the scheduling policy will again either be first come, first serve, or round robin. And historically, there are 100 static priority levels, 0 to 99, with 0 being the lowest and 99 being the highest. And then annoyingly, the normal scheduling that applies to processes, so they'll be under the name Schedge normal. The default priority is a 0, and the priority ranges for those processes are -20 to 19, where -20 is the highest and 19 is the lowest, which is kind of bad. And then because of this, if you're a process, you can also change your own priorities with system calls. So you can use the nice system call to say how nice you are, and we'll see what that means, and the Schedge set scheduler to figure out if you want first come, first serve, or round robin. So let's go ahead and pop over to our VM, because we should actually be able to read this now. So at least the first few columns. So the first column there is our process ID. Can everyone read this, by the way? We're good? Okay. So the first column is the process ID. Again, it's just a number. We know number 1's fairly important. And then we can read the second column. That's just the user that the process is running in. And then the third column, PRI, is the priority, which doesn't correspond to any priority I've shown you so far, annoyingly. It's like kind of a unified Linux priority. And then the last one, or the next column, is the niceness, which is NI, which only applies to normal processes. So this is where it gets kind of weird to explain this stupid Linux specific thing. So how it works. So at the bottom is Linux priorities, and the Linux priorities are always the lowest number is the highest priority. And then it divides them up into 2 regions to kind of have a unified priority. So if you have a normal process, it essentially shifts the -20 to 19 to be 0, like a positive number on the number scale. So it will shift it up in this number line. So if you're a normal process, you will be between 0 and 39. So if I look here quickly at the third column there, the PRI, if that's 0 or above, it just means it's a normal process. It's not a soft real-time process. So if that's the case, then I can actually use the niceness number, and the niceness number is going to be the priority number just -20. So the niceness is just going to be, so a niceness of -20 corresponds to a unified Linux priority number of 0. So does this make sense? Because it's kind of weird. And this is really only so you can read output of top. So that way, annoyingly, so what they do is any soft real-time process is then represented as a negative number. So they took the old priority, which had 0 as the lowest and 99 at the highest, and they just take the minus of that and then subtract 1 to it to put on this kind of unified Linux priority. So an old priority of 0 would correspond to a -1, which is here. And then an old priority of 99, which was super high, corresponds to a Linux priority of -100. So -100 is the highest priority, and you know from reading the priority number, if it's negative, it's soft real time. If it's -100, it's as soft real time as it gets. And if it's positive, it's a normal process, and then I can read its niceness number from -20 to 19. Why it's like that, I have no idea. But does that kind of make sense? Again, there will never be like a question like this. This is just really so you can read the output of top and it makes sense. So let's go through it and see what we can glean from all of our processes. So everything in white there on the right side column, that's a process, and any green text means it's a thread. Yeah.
So is PRI, that's priority number, and NI is the niceness?
Yes. Yeah, so PRI is priority, which corresponds to this Linux priority at the bottom, the unified one. So if it's negative, it's soft real time. If it's 0 or above, it's a normal process. And then you can read its niceness, which would be -20 to 19. But it's going to be the same thing, just shifted by 20. So the default niceness is 0, which corresponds to a priority of 20. So all the processes I see here and all the kernel threads are all just the default priority, which is fairly boring. So let's go ahead and look through them to see if we have something interesting. So here, this RT-kit daemon has a slightly different priority. It's 21, so it is a lower priority. So whoever made this program, it doesn't seem to be that important, except that one of its kernel threads, so it has two additional kernel threads that are here in the green, and one of them, its priority is RT, and that, I don't know why, that corresponds to -100. So, yeah, so RT is real time. So negative 100 is as real time as it gets. And then at that point, I'm pretty sure the niceness number is meaningless if the priority is negative. So the process apparently is not that important, but one of its threads are so important it should schedule it before literally anything else. So that's kind of interesting. Let's see what else we got. So GNOME shell is like kind of your desktop display. So one of the processes aren't that important. It's 39, it's as low as it gets. So it essentially doesn't care. So I have no idea what that thread does, but apparently they deemed it not important. So we can go through. There's another one in Alacrity, which is the terminal I'm using right now. So apparently that's not that important either. Let's see if we can find anything more interesting. There is a lot of garbage here. All right, so tracker miner, apparently not that interesting. VS Code, using 44 gigs of RAM. Hell yeah. So the question is, well, how is it using 44 gigs of RAM? Well, it's virtual, and we'll figure that out later. So it has 44 gigs of valid virtual memory space it can use. Obviously, it's not using that because my computer is not that, doesn't have that much RAM. But it could access it if it wants to. Why it wants to access 44 gigs of RAM, I have no earthly idea. But hey, it does. Let's see. Yeah, they all want to use 44 gigs. Who knows? But they're all kernel threads, right? But yeah, so who wants to program? So everyone thought threads were bad and kind of a pain with all the data races and stuff. Who wants to code VS Code that has like, how many threads? Like 20 threads all fighting over stuff? I don't know. VS Code likes to do stuff. I don't know. So that's a good question. Why does it do that? Because there's a lot. Holy crap. VS Code, please stop. Yeah, so now we get to more interesting ones. So here, priority of 0, negative 20, so that's the highest priority, but still a normal process. But oddly, this one is process ID 2, and init is not its parent, which is kind of weird. So this is an internal kernel thread that only exists in the kernel. So it schedules it like anything else, but this one is always in kernel mode, and it is the kernel. So it has a few high priority ones here. I don't know what they do. So negative 20 NI, so it's 0 in priority, which means it's a normal process. And negative 20 is the highest priority for a normal process. Yeah.
So this is telling you like the relationship of who's the parent, who's the child. It's not telling you like if root process ID 2 is like dependent on the other ones, right?
No, this is just the tree thing here is parent-child relationship. So like this, if I scrolled all the way up, it's parents and knit.
Right. But K-thread is not. K-thread doesn't have a parent.
Yeah, K-thread is like an odd one because it's actually only lives in the kernel. So its parent is technically process ID 0, which does not exist. So it's kind of a weird exception, and but it's just a normal kernel thread, but that's the actual kernel. And it's a user process. Yeah, and we know what init does, right? It forks and waits. And it's just a user process. But K-thread is internal to the kernel. But we can see here, so there's a few good ones. So there's this, which is real time, which is negative 100. And it's a thread that does migration. So this actually, I believe, does the actual context switch because there's one of these for each of the CPUs. So I have 4 CPUs on my machine. This one's real-time priority to do the context switching for CPU 0, then here CPU 1, then CPU 2, then CPU 3, and I only have 3 CPUs on this. So by going through that, we can kind of see how, you can deem how important each thing is.
This is real time, right?
Yeah, so the migration ones are all real time. So the priority there?
No, the output. Is this currently like
Yeah.
the time of your process?
Yeah.
So currently the process is running to display all the other processes that one is.
Yeah. Yeah, so htop, so I'm using htop right now, and it's a process. Like anything else, I don't know where it is because this list is gigantic. But htop would be here. So this is the current process I'm using. So its other columns here, this S column is the state it's in, R means it's running. So it's running because I can display myself
Oh, and everything else is.
sleeping.
But technically, htop isn't like just running continuously. It is being context switched in and out, right?
Yeah, but because it's being context switched in and out, but because it's displaying itself, whenever it's running, it would read what it's doing, which it's running, right? So yeah, htop would if htop doesn't report itself as running, that's something really weird's going on. Because your process that's displaying itself isn't running doesn't really make sense. But everything else is sleeping because all my cores aren't really doing anything. They're at like 1% usage. So something's waking up and doing something quick and going back to sleep. All right, any questions about that? We can now kind of read this now and understand most of the columns. So we'll understand vert column later, maybe why. Well, we'll never understand why VS Code wants 44 gigs of RAM. That's weird, but we'll kind of understand more what it means. Yeah.
Why is some of the time 0? Does that mean like they loaded up and just never ran ever?
Which is 0?
Right under the one that's 36 hours. A trility, like 2 under that, is like 0. Like time, the time scale. So it's 0, 0, 0.
Yeah, which basically means it just never ran.
Okay.
Yeah, so you can. Yeah, I mean, you can create threads that do nothing and wait on something that never happens. Okay, so let's wrap up. So any questions about, we can now read top and see the priorities. So that's kind of neat. So to go back to the Linux scheduler, so we already saw the ON global queue and the O1 scheduler that has like a per CPU core. So now we'll talk about the actual algorithm that they use. So it's something called the completely fair scheduler, and it's fair, which allows for pretty good interactivity. So, So the kind of O1 scheduler has really bad issues with modern processes. It wasn't that bad when it was easy to detect what foreground processes were and what background processes were, because you just had a dumb terminal, so you knew if it was connected to the terminal or not. But if you have GUI applications, you have no idea what is actually in the foreground, because maybe you think, oh, whatever window is focused is in the foreground, but that doesn't mean the user can't see it, and it just kind of gets really, really hard. So the kernel could try and detect which applications are kind of user applications through some heuristics. Maybe you think a process that sleeps a lot may be more interactive, like does something with keyboard input and then goes back to sleep after it updates its display. But it's kind of ad hoc, which just means you're just guessing in the dark, and it could result in kind of unfair scheduling. So to introduce fairness for different priority processes, what you could do, and what they do, is use different size time slices based off the priority. So the higher the priority, the larger time slice you get, and if you are a lower priority task, you get a smaller time slice. So there's also situations where this could be unfair, but in practice, it seems to work quite well. So if you have ideal fair fill scheduling, where you assume that you have an infinitely small time slice, well, then that's simple. If you have n processes, you just give them all 1 divided by n of the CPU time. So if you have 1 process, 1 CPU, it gets it. If you just have 1 processor and 3 processors, or and 3 processes, then they all get 1/3 of the CPU time. So it's just evenly divided. That's as fair as you can get. So here's an example of that where 4 processes come in at the same time at t equals 0, and they have some alternate burst times or complete time they need on the CPU. So 2 processes take 8 units to complete, 1 takes 4, and process 3 takes 16. So here, if we draw that out in kind of a Gantt chart where we're assuming a fair scheduler, we'll just make every column here represent 4 time units just so it's easy to divide everything. So in the first 4 time units, since we have 4 processes active, to be fair, we just give them all 1/4 of the total CPU time, which would be 1 time unit. So they each execute for 1 time unit here. And then for the next 8 time units, they still all exist. They still want to use the CPU. So we all give them 1 time unit again. And we do that a 3rd time, and then we do that a 4th time. Then at this point, process 2 and process 4 are done executing because they only need to execute for 4 time units. So now if we're being completely fair with our 4 time units of CPU time, we would give each process 2 time units. So process 1 and process 3 would both execute for 2 time units because there's only 2 processes now. So they'd go from 4 to 6 time units of execution, and then you do it again. So now process 1's executed for 8, and same with process 3, but now process 1 is done. So we have 4 time units of work, only 1 process left. So it would take them all, execute from 8 to 12, and then go from 12 to 16, and then we'd be done. So this is what you would do if you had 4 processes with varying times and you want to be completely fair. So any questions about how that works? Yeah.
How are they, wait, so how is the jump of 4 happening from 12 to 16?
So at that time, it's the only process left executing. So each of the columns is 4 time units, so it's just taking them all.
So it's like effectively taking 4 CPUs, is that it? Or?
It's taking 4 units of time. So this is all a single CPU.
Okay.
So it's just, I just divide it up just so that's easier to show it being divided.
Okay.
So yeah, so the first 4 time units, I'm just assuming it can switch like infinitely fast. So after 4 time units, they've all executed for 1 because I'm being completely fair.
Okay.
So then after that, when there's only P3 left, it just executes for all 4 because it's the only one left.
Okay. And this is the CFS?
This is ideal fair scheduling, where I just want to be completely fair to everything. So that's the ideal fairness, but it's also terribly impractical because, yeah, so every process gets an equal amount of CPU time. It would boost interactivity and has ideal response time since you're assuming that you can switch infinitely fast. But in practice, this would require way too many context switches. And you also have to constantly scan all the processes, which is order n, which takes a long time, especially if you just want a kernel to do something quick and get out of the way. So but it's a basis for the completely fair scheduler. So this is what the kernel actually uses now. So for each process on your machine, it assigns it a virtual runtime. And then at each scheduling point where the process runs for some like time slice t, you increase the virtual runtime by the amount of time it ran for and the weight, which would be based off the priority. So this is why they use a lower number to represent a higher priority. So if you are a very high priority process, you would only increase your virtual runtime by a little bit. And if you are a low priority process, you would increase your virtual runtime by a large amount. So the property of the virtual runtime is it monotonically increases, which is just a fancy math word of saying it never decreases. It always only grows over time. So it never gets any smaller. So what the scheduler does, as soon as it keeps track of this number, to schedule a process, it just selects the process with the lowest virtual runtime, and that's it. And then it computes its dynamic time slice based off how many processes are running on your machine and what you would do in the case where it was, you made the ideal fair decision. So in this case, it allows the process to run, and then it would run for whatever time slice it decides. And then when that time slice ends, it would have increased its virtual runtime by some amount. and then the scheduler would just pick the process with the next lowest virtual runtime. And to do that, I think you just learned this in another course, red-black tree. So here's where it's actually used. So you get a practical application already, right? Great planning. So completely fair scheduling is implemented with a red-black tree. So it's a red-black tree, and it's keyed by that virtual runtime. So whenever a process ends, or you create it, or it terminates and you need to delete it, that's a logarithmic operation, which is quite fast. And whenever you want to schedule a new process, you just pick the one with the lowest virtual runtime. If it's in a red-black tree, it's 01, right? It's constant time, so it's nice and fast. So in this red-black tree, all the virtual runtimes at a nanosecond granularity, which just means that's the smallest time unit it keeps track of. It doesn't keep track of like picoseconds or half nanoseconds. Just goes down to the nanoseconds. And using this approach, it doesn't actually need to guess the interactivity of a process anymore. It just kind of falls out of what happens. So if you have an interactive process, it typically does a lot of I/O, and completely fair scheduling favors those by default. So if you're waiting on a bunch of input most of the time, you're not running, you're blocked, and then the kernel would wake you up, and you do just a short operation to use that data. So you would voluntarily put yourself back to sleep. You wouldn't use much of your virtual runtime at all, so it would only increase by a small amount. And then that way, whenever you have new data, you're likely to be picked again whenever you're eligible to run, because you still probably have the lowest virtual runtime. And then because of that, and your process exists for a lot longer, it would also gradually over time, if you're trying to model the ideal fair situation, you'd get a larger and larger time slice, and then you would catch up to the ideal. So if you need to do a lot of computation after you get all your data, you would already kind of have built up your time. So this is actually used. Any questions about this? Yeah.
If like the process needed to run for a while, in theory, it could, like if so you have one process that would take like say 20 seconds and a bunch of processes that take 1 second. If the 20-second process ran for a bit, it could get a virtual runtime of like 10 seconds, then be context switched out, another process would run, and that one, like, couldn't you start it out because it would be always going to have that 20 seconds, and in theory, you could have the other processes never quite get to that virtual runtime.
But eventually, if they never get to it and they never get to that virtual runtime, they'll be put to sleep, and then you'll probably have no other option but to run the 20-second one.
Oh, okay.
All right.
So even if couldn't you constantly making more processes that they can start and finish shortly? If you constantly had an influx of new processes that were like only took 1 second to run, they would have the 0 virtual runtime, so they get context switched in first, and then they run for 1 second, so then they're done. And so a new process would come in, and then you could start it out because you only have.
Yeah, but you also kind of base the time slices based off the fair policy, and then you might just fudge it a bit with increasing their virtual runtime by a lot. So there's some fudging details to get around, but this is actually what they implement, and you can see the details if you want to poke around in it. All right. Any other questions? Because that's, yeah, like the issues just pointed out, the actual implementation is going to be a bit trickier than that, but at the core, it just uses a virtual runtime, picks off the lowest one, and that seems to work quite well. Okay, so we saw today scheduling got even more complex. We introduced priority, but also introduced priority inversion. Then we figured out, processes probably fall into 2 categories where some need good interactivity, others we only care about how fast they finish, and then what you could do, separate queues for both, and then you have to schedule between queues. Then we saw what you do for multiprocessor systems that may require poorer CPU cores, which is kind of what Linux used back in the day. We also saw kind of real time that requires some predictability and has some timing constraints. And then we finally saw the completely fair schedule that tries to model ideal fairness, and that's the actual scheduling algorithm that your kernel uses today. So just remember, I'm pulling for you. We're all in this together.